Okay, now for something completely different. We're going from proteomics to metabolomics. There are a few commonalities, of course. The technique is basically the same. We use XCMS, but there are a few fundamental differences between the metabolome and the proteome. With metabolome, we must quite honestly say that the size of the metabolome, the complexity of it is mostly not yet understood. We have some idea of what should be everywhere. We have some idea of what we should see in terms of metabolites in most model organisms. But on the whole, we don't know very much about the metabolome, and it has to do with the complexity of actually identifying what's in there. With proteins, you can still argue where we can figure out the sequence, and the sequence needs to be hidden somewhere in the genome. In the genome sequence, we can do all of it, so there cannot be all that much hidden proteome, even though we've discussed that there are some exceptions to that. But with metabolites, we really don't understand the complexity. There are databases that usually contains tens of thousands of different metabolites, but the only thing that's certain about that is that it's not even remotely complete. When you think about all secondary plant metabolites, for example, we know very little about those. But then there are also more fundamental differences between the proteome and the metabolome that are, some of them are obvious. It's different chemistry. That's sort of the most striking difference. The 20 amino acids are rather straightforward. You know how to connect them, but metabolites can be anything that's more or less chemically feasible. That means that we have a much more homogeneous chemistry on the proteome side, and that has implications also for the separation, for the experimental setup. It is not so trivial to separate all metabolites on one separation system, or outright impossible. When you look at where we should expect to find them, then it's pretty clear that metabolites are usually lighter. They're small molecules, for whatever that means exactly. They're typically in a mass range of 100 to 300 Dalton. Peptides are typically longer, in particular when we're talking about tryptic peptides. Fundamentally, all molecules, all biomolecules are metabolites. Yes?
I don't want to get into a rat's nest, but I'm just curious what the sort of big picture difference would be between Raman spectroscopy and then utilizing mass spec to try to distinguish metabolites or
The role of Raman spectroscopy currently is rather limited when it comes to metabolomics. Raman is a good technique for fingerprinting things, but it is not so easy to integrate that in a high throughput setup. So I have yet to see a paper, but perhaps I missed it, that really applies Raman spectroscopy to a whole metabolome. That is, as far as I can say, not being done at the moment. Raman spectroscopy. Can we take that offline? Because otherwise I don't want to end up doing a physical chemistry course right now. But in one sense, Raman is a vibrational spectroscopy that can be used to identify and fingerprint molecules. That is being used, has been used in physical chemistry for a long time.
So it's not a special mass type of
No, it's optical spectroscopy.
just utilizes
Okay, lipids, sugars, that's all metabolites, but traditionally we do not include them in metabolomics. These are distinct fields. People are talking about lipidomics, glycomics, but everything that you know from your biochemistry textbook, ATP, ADP, nucleotides, these are all considered metabolites and are interesting to metabolomics. Just like in proteomics, we have two fundamental approaches on how to analyze a metabolome. And you can either do target metabolomics, and that is very popular. There are companies where that is the business model that just rely on quantifying a small selected subset of the metabolome really well, but only that. So as long as you're interested in, say, a central carbon metabolism, that is fine. But if you're looking for something outside of these well-trodden pathways, then targeted metabolomics is probably not going to do it for you. In this case, you have to go to non-targeted metabolomics, or metabolic profiling, as some people call it. There's some ambiguity in the terms. And there you try to see as much of the metabolome as possible, usually thousands of metabolites. And again, we have to distinguish what of these we can quantify and what of these we can identify. And today we will be talking mostly about the quantification, and that we can easily do for thousands or even tens of thousands of metabolites these days, but identifying those is a bit harder. And that has to do with a more diverse chemistry because we don't have a linear sequence that we can easily pull out.
For non-targeted metabolites, are you able to essentially predict what the chemical structure was sort of de novo instead of having to see the fragmentation pattern beforehand? Like instead of having to match it up against the library?
That's what we will discuss tomorrow morning.
Okay.
The short answer is yes, you can, but it's not so easy. It's a similar situation than in proteomics. Library search is always easier than full de novo, and that's also true for metabolites, or even more true for metabolites. From the idea, label-free proteomics and non-targeted metabolomics are very similar. Because for the quantification, you don't really care what it is that you want to quantify. The only difference is that you're dealing with compounds that have a different chemistry. We will see where our approaches for proteomics break down because of this particular reason. So the overall workflow should be the same. We do a feature finding step, we do map alignment, we do feature linking. And at the heart of this algorithm, you don't have to change all that much. You can still try to find mass traces. You can try to assemble them. But there are differences because the isotopic patterns are going to be very different. And why is that? Because it has a different chemistry. This average gene describes amino acids, and if you're looking for amino acids, that would still hold. But you can imagine that there are metabolites that contain halogen atoms. And these have very different isotopic distributions. And they will look very different from what you're used to from peptides. Also, the mass range is different. That has also implications. And the charge states are, of course, different. On the whole, however, we would still do the same overall setup. We have the same terms that at least we would like to use. We have a map that is a 2D data set of an LCMS run. We have a feature that's the sum of all signals that is now caused by one particular analyte in one specific charge state. And that's a bit different to proteomics in one specific adduct state. Because metabolites usually form adducts, ion adducts. And those can give rise to different features as well, even though they come from the same metabolite originally. And feature finding is then again the task of identifying which of these peaks correspond to one particular feature. You've seen this figure already. We try to find features in one map, we align them, we link them, and now we try to identify not a peptide sequence, but actually a metabolite ID. And again, we want to quantify that based on the volume of the feature finding algorithm. So when we try to design a feature finding algorithm for metabolomics, we need to drop this average gene hypothesis because it's just not true. Metabolites are chemically much more diverse, and even worse, they have a smaller range of, they have a smaller mass, and that means the number of atoms in there is reduced. So you have a different combinatorics. It doesn't average out as much as it does in larger proteins. Feature finding algorithms are always rather sensitive when it comes to the choice of parameters. That is something that you should keep in mind as well. Many of them have dozens of different parameters that you need to tune to your specific chromatographic conditions, to your specific metabolites as well that you might want to find. And for many of these algorithms, sensitivity is an issue. Just like in proteomics, it is not easy when to call a peak a noise peak and when to call it a feature, low intensity feature. You might know that there are a few tools for metabolite quantification out there. Probably the most popular one is XCMS. That's a bioconductor package, and many people are using that. It's actually working reasonably well. Here the key ideas, and there are different algorithms in there too, but the key idea is to extract mass traces by binning peaks with respect to M over Z. So they simplify the overall spectra, and then detect peaks in these mass traces by just doing standard signal processing on these bins. Then these mass traces are aligned using non-linear dewarping, so you can have a look at that. Basically, the raw data will be filtered, peaks will be identified, and peaks here means along the ion chromatograms. These are then integrated. And one of the things that you notice when you go over that, there is no notion of isotopes, no notion of features in there. XCMS in the initial version really looks only for mass traces. And that means you will not get a table that contains all the features, but you will actually get list entries for every mass trace. So if your feature actually has monoisotopic +1, +2, you will get 3 entries that are hopefully highly correlated in your output. There are other tools like Camera that then take these mass traces and try to assemble them into features, but that is again a different processing step. So XCMS has been the quasi-standard for LCMS, and you can actually use that from 9 if you want to, also if you want to compare that. People have done that as well. For many tasks like biomarker detection, you can stop at that level. You don't really need to find the features. You can just say, I look at the mass traces, and that will be enough. If I want to validate a biomarker, I have to follow up anyhow. But since these instruments are getting more and more sensitive, you would just end up with an overload, because you have a whole, of course, you have at least twice as many of these mass traces than you have features. So proper feature detection is something that reduces the amount of data that you get out of these data tables. So if you want to continue using OpenMS, then there's a tool that's called Feature Finder Metabo. It was published a couple years back. And this uses the same ideas that we discussed for label-free quantification. So it starts by looking for mass traces. It then looks for isotope patterns between these mass traces and tries to assemble them into features. But there are a few fundamental differences, and the differences lie in the way the mass traces are detected. We do that in a more sophisticated manner than for the proteomics feature finder, and in the assembly, because in the assembly we can no longer assume the model that we have for proteins, the average gene model. The output, however, is going to be almost identical, because it's still looking for features, and it's going to give you a table that contains for each feature the retention time, M over Z, and the intensity that is required for the quantification. So fundamentally, what comes out of this metabolomics feature finder can be processed in exactly the same way as you can do it for a feature list out of proteomics. Downstream, what you need to do in terms of identification, of course, will differ quite a bit. But if you're just looking for differences, it's just exactly the same idea, exactly the same concept. So what does the algorithm do? So the first step is again a mass trace detection. So we are looking for adjacent peaks. And there is something that you can see in this figure that's a bit subtle, but that is essential. So when you look at this mass trace, you actually see that they start to scatter about towards the end of the mass trace. And this is experimental data. That's what you would observe. Why does that happen?
They have lower intensity.
Pardon?
The edges, they have lower intensity.
Yeah. So it just becomes harder to correctly identify the accurate position of the peak in the mass spectra if you have very low intensity peaks. So the highest mass accuracy you actually have somewhere in the middle. And this is something that you can use because it tells you the mass trace is almost over. Yeah, if the peaks start jumping around, then you can stop looking for them. And that's something that this algorithm exploits explicitly. So we try to find these mass traces. I'll show you details in a minute. We then have a huge list of these mass traces. We check these mass traces whether they actually contain overlapping metabolites in the same way I described that earlier. We split these mass traces if that happens. And then we assemble mass traces based on their spacing, on the co-elution, and on the isotope pattern. So there's a scoring scheme, a very similar manner. We try to bring them back together based on a hypothesis that explains the signal best. So how do we do the mass trace detection? This here is an example. You can see quite clearly what I described earlier. We have the retention time along the y-axis, m over z along the x-axis, and this here is probably the apex of this mass trace. And as you go down in intensity towards the beginning or the end of the elution profile, you see how these peaks start to scatter around. Now, what we're trying to find is a mass trace, and a mass trace is just a list of peaks that we have found, and peaks are defined by their retention time, their mass to charge ratio, and their intensity. So this is what the output of the algorithm should be, and we start with a rough idea of when two peaks in adjacent spectra should belong to the same mass trace. And they should belong to the same mass trace if they are no further apart than excuse me, what you would expect from the mass accuracy of the instrument. So if you know my instrument is going to be accurate by about 2 ppm, then that is what you start with. Now the trick is that we update an estimate of this accuracy using online Gaussian density estimation. And that sounds fancy, but it's actually reasonably straightforward. We just start with an estimate, initial estimate, and let's assume this here is our nominal instrument accuracy. We start with the most intense peak and say this is where this starts, and then we can look up and downstream in adjacent spectra. And we look, is there a peak that is included into our current error interval? Now the nominal accuracy of the instrument, that is not what you will actually see at this particular position. That will vary along the spectrum. So usually the reproducibility of that particular peak between adjacent scans is much better than what you would expect from the mass accuracy of the instrument. So we find that this peak here is probably part of the mass trace as well because it is still within our error bound. So we include that, and now we can get a better, tighter estimate of the error. And we update that. There's a simple equation that updates the estimated error. And as you add more peaks, and these peaks are within a narrow interval, these error bounds tighten. So we check the next peak that is still within our error interval, and you see this, the width of this interval goes down until we hit these peaks that are starting to scatter around. And that is when the algorithm figures out, well, all of these peaks have been within 0.1 ppm, and suddenly these guys won't fit anymore. So what the algorithm really does is it estimates the local error along this mass trace and discards anything that is inconsistent with what it has seen so far. And that's a very natural way to abort the mass trace detection towards the ends.
Why does it
Say again?
Why does it trace the local error when it goes down? Why does it use the local error for the marginal judgment?
Because that is more selective than having the nominal mass error. The nominal mass error is just too big. The local error is usually a lot lower than that. And that is also interesting because it tells you, it gives you tighter bounds on then assigning mass traces later on. Yeah?
Do you take reduction time into account when you do this?
Not yet. Not yet.
So it's only based on the mass of charge?
Yeah. This is just,
Yeah, one question if I understood correctly, but what if there's outlier somewhere actually very close to the apex? Would that throw away the algorithm at all?
yes and no. So what you describe is something that happens and has happened to us in TOF data quite a bit, because you can have saturation effects that change the shape of the peak. Note that these are mass spec peaks, not chromatographic peaks. So we call that the banana effect, because what happened is that the saturation shifted the masses in the high intensity range to the right. Now what happens if you do that in this framework? As long as this shift in the high intensity peaks is below the nominal mass accuracy, it will not tighten the bound. Because these peaks sort of shift towards the left, so you get a pretty big variation, and only if you go lower in intensity it will actually tighten the bound. So as long as these deformations are below the nominal mass accuracy that you start with, all is fine. But that is one of the things that you have to test. And if you see that phenomenon, you just have to open up the initial mass accuracy. Okay? So the next step is then, once you have these mass traces, you split them. That is a simple peak detection. We determine the full width at half max. Note that in this case, we do not assume that there is a peak shape. So even if you had rectangular peaks, like you get them from CE, for example, the algorithm would still be able to find them. It will not be very happy, but it'll do that. So it does not assume a model of the peak shape in contrast to the proteomics feature file for various reasons. Next step is assembling these mass traces. How do you do that? What you expect is such a picture. You have a monoisotopic, you get a +1, +2 that are induced by isotope satellites. But how do you figure out, I mean, here it's pretty obvious, but how do you figure out in a larger data set which of these come together? Well, what do you know? You know that they should co-elute exactly because they come precisely from the same molecule. So that is a prerequisite. And of course, you know the expected difference when it comes to mass to charge. So what we do is a scoring that is based on 3 components: mass to charge, where we assume that we have a distance that corresponds to one of the possible charge states. And again, we enumerate multiple charge states. We have a scoring function that includes the estimated mass errors that we have determined locally. That's where they come in handy, because if the mass difference is a lot bigger than what you would expect plus the estimated errors, then it's probably off. The second component is the retention time shift. So we determine where the max of these elution profiles is. We have a Gaussian error model, and again, if they're shifted by too much, we would consider them not correlating really well. And the third component is probably the most interesting one, that's intensity. And now the question is, how can we rely on intensity if metabolites can have vastly different isotopic envelopes? So what we did there is we took 24 million possible compositions. So not just metabolites from known metabolite database, because we didn't want to exclude specific compound groups. Instead, we took 24 million compositions of possible compounds there is a set of rules in chem informatics, 7 golden rules that permit the construction of hypothetical compounds just based on plausible chemistry. Probably would call it that. Plausible reactions that can happen. And you can just construct a huge space of possible things. And what we then did is we subsampled that and trained a support vector machine to recognize these patterns. We have no idea what these patterns really look like. I mean, we could look at them, but we just rely on the support vector machine to recognize a metabolite if it sees one. I don't try to define it. It's like this pawn detector. I don't know what it is, but I recognize it when I see it. In the same way, we can detect metabolites without really having an explicit model of what these isotope profiles look like. And this support vector machine adds to the score. If it's within certain bounds, it says keep that pattern, otherwise it discards the hypothesis and we score the next one. And that works reasonably well. The question is, how well does that work? And it turns out that benchmarking these algorithms is something that is not trivial. We didn't talk about that earlier when I was talking about proteomics, but I want to give you some idea of how you can actually benchmark quantification algorithms. So the analytical chemist would just say, well, let's see how the linearity of the whole thing is. So one thing you can clearly do is an experimental validation. You say, I take a complex matrix, I spike in 1, 2, 10 metabolites, and I ask the algorithm to recover the relative intensity. That's what we did here. We have 2 compounds, reserpine and terfenadine. We had, I don't know how many, 15 different concentrations. For each of these concentrations, we measured the full LCMS run. And what you can see is that this works quite well over about 3.5 orders of magnitude. So we have a reasonable linear range. You see that there in the lower range, there's something going on. But on the whole, if you got an R squared of 0.997, you would argue that is not too shabby. It's actually a bit harder to determine how sensitive and how specific this algorithm is. Why is that? Or what is sensitivity and specificity in this context? Well, we're trying to find features. So sensitivity means that we want to know how many of the features that are true features can be found. And specificity means how much of the stuff we have found is really a feature. And just like you probably know that from machine learning, you can easily construct something that gets a specificity of 1 or a sensitivity of 1, but the real art is getting something that has a sensitivity and a specificity of 1. Now, what's the problem with metabolomics when you want to determine sensitivity and specificity? Well, the problem is you don't have a ground truth. You could argue I just take 100 metabolites, I pipette them into buffer, I measure that, and if I find these hundreds, it's fine. What's the problem with that approach? Could happen, but that's usually not the problem.
Matrix confusion, matrix suppression.
No. So let's assume you take one metabolite, pipette that into buffer, and do a measurement. How many features would you get? No. It's going to be thousands. Because already the blank will contain 4,000 or 5,000 different things. The problem is really that mass specs are so sensitive that you cannot really, well, not with reasonable effort, construct a sample where you have a known ground truth. And if you buy a metabolite from Sigma or whatever, and it says 99.9% pure, that means you have already 100 different things in there that are left over from production, from degradation, from whatnot, from the vials. So it's actually very hard to know what is not in your sample. So one way to do that is actually to do a synthetic benchmark set. Synthetic meaning we simulate all the data. And that is something that you should keep in mind. That is a very viable approach. It's sort of frowned upon by many experimentalists because they can't believe that you can simulate the data in a way that is halfway reasonable. But we did a very simple experiment. We took a paper on metabolomics that had a very complete set of metabolites that they detected and analyzed. And we simulated the retention time, or we had the retention time from the paper. We had the composition from the paper, and we just simulated the MS spectra. So one part of OpenMS is also an LCMS simulator. So if you want to generate synthetic data, you can just put in the peptides or metabolites that you expect in your sample, the relative intensities, and it's going to produce something that looks very much like an LCMS data set. So we actually showed the spectra to experimentalists. We fooled some, not all of them. As you would expect, there are some differences between the data, but you can tune some things like the noise level, like the intensities. You can tune that in a way that you cannot do in an experimental setup. And with that, you can now, because you know the ground truths, you can now ask this question, how specific and how sensitive are we really? And what you can see from the comparison is that on this data set at least, things are not looking too bad. So we got a recall of 96%, a precision of 97%, so that's pretty decent. And that also answers a question that arose when we did that in an experimental setting. The other experiment you can do is you take the same sample and measure it a couple times. Technical replicates of whatever it is. Doesn't really matter what it is. So in this case, we measured the same sample 33 times. And what you can see in this figure is the number of detected features on the y-axis, and on the x-axis in how many of these measurements it was found. And the two different bars correspond to two different algorithms, XCMS and camera and the feature finder Metabo. So you can see that about 800, 900 metabolites were found in between 30 and 33 of the measurements. And what is a bit scary is that you find about 5,000 metabolites only in individual measurements. So what's your interpretation of this figure? What do we learn about the algorithm? Detects a lot of noise. That's one interpretation. So what you're saying is this light gray bar, this algorithm is trapped because it pulls out 3 times as many of the things that are present only in one sample, and because they occur only in one sample, they should be considered noise. That's what you're saying, right?
I don't want to say that about your own.
No, I mean, you can say about my algorithm anything you like. I'm sort of.
Would you say that the fact that the ratio stays consistent between feature finder and XCMS throughout, even for the high end of finding the same ratio in nearly all the sample runs?
Yeah, that's interesting. So let's look at the right-hand side of that. If you look at this, you would argue where the light gray bar, this algorithm is superior because it can reliably identify twice as many features in all samples. And both statements are kind of true. And this is why I showed you this comparison on the simulated data set, because just by looking at this figure, you cannot really tell what is going on. So these guys are not necessarily noise. If you go into the raw data and look at them, some of them have perfectly reasonable illusion profiles. They look like decent features. There's something there. This is basically the stuff that is borderline, that's on the border of the limit of detection. So sometimes you see it, sometimes you don't. And there's lots of that because you have many things that are present at very low concentration. Whether you call them noise or whether you call them low intensity features, it doesn't really matter a lot. What you can clearly see from the ratio is that on the whole, one of these algorithms is more sensitive than the other. It just pulls out more stuff from the data. If you see this here, if you look at the consistent features, you can also see that it's more specific because it finds the same things over and over again. But whether what is really going on, that is something you cannot easily tell just by looking at experimental data. All right, so how do you do that with OpenMS? I pulled out a workflow we used in a diabetes-related biomarker study, just to give you some idea of how big these workflows can get. So don't worry that you can't read these individual nodes. This here is a workflow, and I tried to color the background of the individual parts of the workflow so that you get an idea of what is really contained in full analysis of this data. So in yellow, we have the initial data pre-processing. In purple, we have some quantification. And up here, we have then some more advanced things down to reporting. So let's look at the data processing. This looks more or less the same as the label-free pipeline. So we start with a bunch of files, MZML files. We have a loop that applies the feature finder metabo. That is the Metabolomics feature finder. We sum that up. We do an alignment. We do a linking of these features. And then we can throw that out as a text file or as a consensus file or whatever. So this is exactly the same as for label-free quantification, with the exception of this algorithm that is a different one. But otherwise, same idea. So what we can do is we start with 5 controls, 5 samples in a reduced study. You have to set the parameters of this guy. And this feature finder metabo has very few parameters. It basically needs an estimate of the chromatographic peak width, and it needs an estimate of the nominal accuracy of the instrument. The rest is more or less irrelevant. And you've seen from the algorithm already that even the nominal mass parameter only needs to be a rough number because it's going to estimate the local density, local error anyhow. What it produces is then such a feature table. That is what you have here at the end for each feature. And we don't know what it is, but for each feature we have the centroid retention time, mass to charge, the charge, and the intensity in the various samples, and that is the distinct column. So what we do in NEU is then massaging these tables. So that is a bunch of nodes that are not OpenMS nodes, but are actually built-in NEU nodes. So just that you see them, you can filter out columns, remove the stuff you don't care about. You can rename these columns so that instead of sample 1, it says control 1 or control 5 or whatever you have. You can manipulate the various entries. We can split them and do things like imputation of missing values. We will look into that in a minute. What that does is gives you a table where you actually have proper names, where you can and you can take it from here and export it to R or visualize it in Excel if you like. We can then do some more statistics. So what we do here is we make use of the embedded R nodes. So you see these nodes here that are R snippets. In the first one, we do the intensity normalization. Then we do hypothesis testing, a simple t-test for these two groups, control versus normal. Yes?
I'm just wondering, did you
Yes, we did. But for simplicity's sake, I'm not going to talk about that. You need to correct for multiple testing, and you can make a QQ plot or you can make the box plots. You just hook them up to the output of these nodes, and that's already giving you some idea of what's going on. For example, you can see that, yeah, the normalization, that looks okay. There's nothing funny going on here with any of these runs. So that's sort of a built-in quality control. And in the QQ plot, you would see actually there are a bunch of metabolites that seem to be differentially regulated. Then we can do Metabolite ID. As I said, I will talk about that a bit more tomorrow morning. Suffice to say that in this case, we do in parallel the spectral matching and accurate mass search, and these results will be joined and produced and entered in one table per feature, so that you have at least identification hypotheses. And here it comes in handy that NEU was actually developed originally for cheminformatics, so it can natively render structures of metabolites, which is kind of neat, at least for chemists. You can just put structures into these tables and deal with them as is their proper, as if they were numbers or strings or anything like that. So that's kind of cool, and that is what we're going to do in the hands-on session. And then tomorrow morning, so please bear with us. Tomorrow morning we will talk more about how to identify these metabolites, which is still a pretty much a difficult and partially at least open question. All right. With that, I'm through. Are there any further questions? Yes, please.
So how is this workflow going to work for a two-dimensional LC with two retention times will be there, or two-dimensional GC that I'm looking into whether two retention times will be there?
Well, you can process them independently, and the problem really is how do you merge them afterwards if you have, and that's going to happen if you have metabolites that occur in multiple fractions. So the way to do that is to sum them after normalization, but generally you can process it in the same way.
And there is negative mode proteomics, right? So it's going on, they've been proposed. So why it didn't take off? And what does it help with the negative mode proteomics?
Negative mode proteomics.
So you capture all those in the negative ion mode, or the highly charged ones in the negative mode.
So we're talking metabolomics here.
Oh, yeah. But this question is in the
Yeah.
So
We don't care whether it's negative mode or positive mode, so we do both. And you can do, all sorts of metabolomics. You don't even have to do LC. You can also do direct infusion. We also have workflows for that. It doesn't really matter. You need to know. You have to be a bit careful when it comes to identification, because evidently there you will have different adducts. You will have there's different things that you see. But it depends on what subgroup of the metabolites you're really after. Because some of them are obviously going to occur in negative mode, others more likely in positive mode.
Just two questions. So, as far as I understand, the graph that you showed, the algorithm that you have, in principle, you run like 33 or 30 to 33 times the same sample,
Yeah.
and then you found like 900 compounds that is present in those like 30 runs, right? So in principle, I would understand that you have to run at least one sample, at least like 30 times or 15, or what's the borderline that you have to run? Because in principle, in a practical view, so the proteomics you run like 1 or 2 times or 3 times.
Yeah, that's what you do. From proteomics, this would look exactly the same.
Mm-hmm.
There's no fundamental difference. So what's really going on? It's actually an interesting point that you raise. What is going on the left-hand side here? As I said, this is the stuff that is unlikely to be detected various metabolites or the various peptides of having different detectabilities as a function of their concentration. So this is a low intensity stuff and or the stuff that is hard to detect. So it has a low probability of being found in every run. So if you care about this stuff, if you really want to find it, you actually have to run multiple times. But it's not going to help you because this is stuff that you will not be able to quantify. But in the same way that identifications, particularly false positive identifications, accumulate as you measure the same stuff repeatedly, you will find low intensity, funny features as you accumulate over multiple runs, independent of whether that's proteomics or metabolomics.
And another one is just principle proteomics as you're integrating or the under the curve area, just like consider the node TIC or the T. In this case, in proteomics case, usually you perform like protein quantitation, like whole protein quantitation to know, especially in labor-free, how much you're loading to your column or to the run. So generally, you can say that there is like 1 microgram, 1 microgram or 2 micrograms on the column. But how about this works for metabolomics? How do you quantify it before, and you know that you're injecting the same amount to compare afterwards? You know what I mean?
You don't. You
So
don't.
how do you relatively quantify one common component?
Well, you do that just with normalization afterwards. And it's not as big a problem as it is in proteomics because you have fewer processing steps until you come. You don't have to digest, you don't have to precipitate proteins. And all these steps that add to this error that you would do in proteomics, that is not present in metabolomics, or at least not to that extent.
So at least in lipids, when you kind of run an internal standard for every class of metabolites, so I imagine it's the same for metabolomics. So does this algorithm find your internal standards that then you can just normalize per class later in the pipeline?
No, I wouldn't recommend doing that.
Okay.
Our experiences with internal standards were rather poor. I don't think it's going to be really helpful. It depends on what you really want to do with it. If you use internal standards to normalize your quantification, then usually you're better off without internal standards. And you can think of that in terms of statistics. You have perhaps 10 internal standards. People rarely add more than that. And that gives you 10 measurements. But if you assume that you can see 50,000 or 10,000 metabolites, if you normalize then with a subset, say 500 of those, that gives you much better statistical power to normalize your samples relative to each other than these 10 internal standards.
So it's because measurement of internal standard has an error?
Could you speak up?
Is it because the measurement of internal standard has an error and that's why you sort of...
Yes, and also the process of actually adding the internal standard adds an additional error. So we tried it. We had quite a few experiments, and in every case, working without the external standards gave us better reproducibility. But that's just in our hands, different data sets. If you do it right, I mean, in theory, internal standards do work, and there's nothing wrong with them, but they're not as helpful as many people seem to think.
So for those experimentation that you have already figured out to differentially express metabolites, what are the best techniques on how to validate them?
How to validate them? Well, that depends on your metabolite and what you want to do. one way to go forward is, of course, to do targeted metabolomics. That is reasonably straightforward. You can use the same techniques that you use in proteomics, MRM, PRM type of techniques. You just need to be careful that you do that on a different set of samples, different cohort. But that is the approach. But of course, you can also use other orthogonal techniques. It doesn't have to be mass spectrometry. It depends a bit on what you find. It could be that you also develop an antibody-based test for that to validate that.
So how big is the problem of peak weight because the dynamic, the wide range of metabolite abundance, like a glucose is present in 1,000 times more as compared to a small antibiotic. So how you define that peak weight for peaking?
Well, you need to be careful because the concentration, I mean, the analytic concentration of glucose does not mean that the peak is going to be exactly the same height. Yeah? So actually these different specificities, these F factors, they level the playing field quite a bit. That being said, we have a large dynamic range, and if you are trying to capture things that are like 3-4 orders of magnitude different in terms of feature intensity, you will have a really hard time. I think 2-3 orders of magnitude dynamic range is something you can easily do, but anything beyond that is going to be really tricky. Okay, no further questions, then let's do some metabolomics.